Welcome, everybody, to 52 Living Ideas. This is the Bucky Inspired series that we do in collaboration with the Greater Philadelphia Thinking Society. I'm honored to have Don Briddell back on talking about Tometry. This is part 2 of the presentation. If you're watching this on video, please watch the part 1 first and then watch this one. Now, what Don is going to do for people who are listening to it live, he's going to give a quick recap of the first part and then dive into the second part. After the presentation, we will do, please keep track of all the questions you have. There'll be plenty of time for questions, comments, etc. And then I'm hoping that we have time for Don to show us how to actually build a model or a field structure. All right, Don, so with that, let me hand it.
All right, well, thank you all. I'll run through this first part just to familiarize what's said so far. And I think this first part was describing more about the why Tometry was needed as a new geometry that would explain this family of structures that Stanley Wysocki and I discovered back in 1965 when we were students at Pratt Institute. This was our thesis project. And after graduating, this was during Vietnam, we went our separate ways, and I ended up in the Peace Corps and going around the world and stuff like that, and never got back to the States until about 5 years later. But I was working on this the whole time. And what was the challenge was that Stanley and I wanted to took on the challenge of let's do a form and structure theory. It hadn't really been done. There had been some attempts at it through the years, but a comprehensive field and structure theory was still not there. And I remember Stanley and I were looking out our window, looking at all the endless forms that you could see out of any window. And this happened to be in Brooklyn. And we were thinking, how are we going to find out some way to organize the plethora of images that and forms there are in the world? Music had a structure. Everybody could write music and understand it, but there wasn't a structure for form and structure for matter. And so we began through the inspiration of Buckminster Fuller, Kenneth Snelson, and our faculty teacher, Bill Katavalis, to start working with traditional geometries and the geometries we found in the literature. And what we discovered was that all of these forms were really basically solid geometry. And we started our investigation by looking at, well, what's a line? What does line represent? And what is action? What does action mean? Those basic definitions. And physics had already decided that the entire universe is energy in two forms, bounded and unbounded. Boson and fermion, it was called. And so paying some attention to physics as we went along, I became very interested in the physics aspect of it. So I started looking at the forms that we were playing with in terms of, well, does this have any relevance to physics? And it wasn't until one night Stanley and I were looking at a cube that we had made out of wire, shiny wire, hung in a room by one of its vertexes with a thread, and it was slowly spinning. And we turned on a flashlight, and we watched the gleam of the light move along the members of the cube, and noticed that when it got to the from one vertex, when it got to the other vertex, the little gleam would shift to another line on the other side of the form and start going back the other way. And we thought, well, let's link the two together so we can get that little gleam going around. And before you know it, we had put this field, what we now call a field, around this cubic form. So that gave us an insight into what maybe is going on in the objective form world, that there was a field of energy that is creating that effect of being a solid geometry form. So the first form we came up with was called a structure, and I'm going to skip over all this stuff. Here we were exploring what structure was, but let me get to this form here. Here on we have two tetrahedrons where the edges of the tetrahedron are circuited together so that they form a loop made of 3 loops, define that tetrahedron. And let's see, I have these models here, and I'm wondering maybe I should just switch into the models.
Yes, Don, if you could stop sharing for a second so people can see.
Yeah.
You. Okay, wonderful. And if you could.
Okay. The form we came up with first, by the way, I'm sorry for the lighting, but can you believe it? Both of the big fluorescent lights have gone off and aren't working, and I've got this dinky little light bulb here. I mean, today has been a day. So here we have a tetrahedron in the center, connected by these tubes, and the connection reveals that the tetrahedron can be made with 3 loops that are looped together and knotted. And there's no glue or anything holding this together. I can spread these things apart. What's holding it together is torsion. These bent loops want to unfold into a normal circle and relieve all their stress. But each tube is trying to move in a different XYZ axis. And they are, one tube is being blocked by 2 others. And so we end up creating a tetrahedron made of 3 loops. And then we discovered that any form, any polyhedra, which is any 3-dimensional form in the universe, can be made by loops, by interacting loops. And I have done some of the solids in this loop, enough to show that this does actually occur. So now we've got the idea that loops interacting generate the form of any polyhedra. And so what is a loop? A loop is an action event that has been invested with torque, so it wants to unfold. And by interacting these loops of energy, we can create any 3-dimensional form. And this is the eureka moment we've been waiting for to now investigate all the various aspects of form. But my interest in physics said, okay, this is an interesting tometry that's going on. Does it relate to the actual physical world? Can we use these models to quantitatively and qualitatively replicate in the macro scale forms that are found in the micro scale of particles and atoms and molecules? And the answer was yes. And so in a book that I wrote this book called The Particle Hierarchy Paradigm. And I explain in that book how loops quantify and give us the same ratios between number sets that physics is using electron volts. And so now we've got a physical way to model what's going on in the energy of a particle, an atom, and a molecule. And if you had the time to build it, any other form right on up. And so this book charts all this out and shows that all the particles, and there's three stable particles, then there's the neutron, which is a summation of all those three, can be modeled, and their mass and energy values can now be determined by the number of loops and the number of times those loops twist in order to complete their circuitry. And those numbers relate right back to what physics has found as the energy values of the different particles. And they're using, at first, when they first started doing this, they were using the electron as the base unit. How many electrons are in the proton, for instance? Now they're using it, now they're studying this in terms of its energy. Since E equals mc squared, you can do it either way. And the energy turns out to be the number of loops. This is for a mass, the number of loops times the number of twists squared. And that will give you the same numerical relationships as found in all of the particles. So that is one significant achievement of that. So once we got a model for a particle, this is the particle model, where the polyhedron in the center is circuited together with loops into an object, a field object, which is the tetrahedron, and the field surrounding and creating that object. So from there, we thought, well, what does an atom look like? If that's what a particle looks like, what does an atom look like? And here's that model. This is a tetrahedron inside of a tetrahedron. So the inside is the nucleus, and this field around it is the energy field, which in physics would be your electron cloud. And what is interesting here is that this is still only 3 loops. And the inner triangle and the outer triangle are simply circuited each other. So I didn't add any loops. I just circuited the inside triangle to the outside triangle to get that field effect. So in an atom, if you wanted to find an electron, you would look at where these 3 loops intersect out here in the distal cloud. And if you wanted to find out where the proton is, you look in the internal triangle and you see how that forms. So let me go back to the shared screen. So this is Joe Clinton's computer animation of 2 tetrahedrons. And if you cross your eyes and look in the middle, you can see what it looks like 3-dimensionally. It'll make a stereo image. And once you get used to this, you can just do it in snap. Now, the thing to note about these forms is the intersection of these loops and how they have a handedness. This loop is rotating counterclockwise, and this one too. These are the same loop, only photographed a little bit off from each other so that you can get the stereo effect. So this is a counterclockwise rotating form. And you could build it just the other way. You could make this by circuiting it in the reverse. This would be a clockwise rotating form. So this is the explanation of spin. And physics has never had a really good way to describe spin, because spin is often thought in terms of just a body rotating like the Earth rotating the sun, spinning in that sense. But this is a three-dimensional spin. And this is the way it would look. Now, Joe Clinton later discovered this form down here, which is a diploid structure. These forms up here are condensed structures. So this form is spherical, and the little triangle intersections are occurring on the surface of this sphere. So we have two forms of structure, the diploid and the condensed form. And I haven't investigated hardly at all what's going on with the diploid structure, only in that this form is one that can increase in size, whereas the bounded ones are confined to a specific domain. Let's see here. So here's the picture of the three loops making the tetrahedron. These are four loops making the octahedron, and you can see the octahedron inside of there. It takes four loops to do that. And the dual of that is the hexahedron, or the cube. This also needs four loops. Then you go to the icosahedron, and you need six loops, and there are these different colors here. And I left a solid icosahedron in the center, just so you can see what it looks like as a solid. And then looking at just a single loop, noticed that this forms a torus. You can see it quite good on this to the right. So what you're really doing here is you're interacting various torus structures, and they are creating a nucleus that has, in this case, the icosahedron. When I add all the other loops, then it looks like this. And the dodecahedron is the dual of the icosahedron, but here the same number of six loops differ because it takes two revolutions of the loop to complete itself. Here's the blue one going around, and it comes around again as blue before it hooks back up into the first one. So the difference between an icosahedron and a dodecahedron is the number of loops. And as I mentioned before, every form has a specific number of loops and a specific number of twists those loops have. If you know those two things, you know what the geometry of the form you're looking at has. And that is something that physics hasn't really known, because what this really is saying is momentum and position can be known at the same time once you know what the structure is. And that's the problem with physics, is that you can't know both of them. It's called the uncertainty. It's called the uncertainty principle, in that if you want to find out where something is in physics today, you have to stop it to find it. But if you stop it, you don't have any more momentum to look at. And the other thing you can do is check the momentum. But if you check the momentum, we're talking about energy moving at the speed of light, or near about, so that it seems to be everywhere. And that's the solidity we find particles exhibiting. But if you looked at the internal structure, as we're doing here with the field structure, you know where the energy is moving and how it's moving. And another important piece of information this gives you goes back to the issue that physics ran into with determinism. They got down to the atomic and particle level, and because of the uncertainty principle, they found that they couldn't they couldn't identify with certainty where an electron was, for instance, in the electron cloud. So they had to approach it through statistics and probabilities. And so quantum mechanics became really the math of probabilities. They knew it was probably more certain to find it here than there, and they could build up a generalized picture of where the energy was. But with a field structure, we can actually model it here in the macro scale. And so where an electron is, for instance, in this particle here, we're dealing with finding the field particle at these points of intersection here. And there's 20 of them in a dodecahedron. So that means that this is a qualified determinism approach, whereby a particle is distributed throughout that cloud, but it's only found in certain places. And if we could cool down an atom to its minimum rest state, we would find that if you want to find where the electron might be, you would look at these points of intersection. And if you didn't put your measuring device at that point, you wouldn't find anything. It's where the intersections occur is where the form manifests itself. So the difference between regular topology and tometry is that this is considered a three-dimensional knot in topology. And this is a three-dimensional knot in field structure theory, in tometry. The difference is this knot does not define space, but this knot does, because it defines a tetrahedron, the smallest division that you can make in space. So this is a knot in space, and the structure here is a knot creating space. That's the difference. So I think this is about where we left off last week. And so to finish up here, I'll start reading some more of this. But let me stop and just ask, is there anything that I could do to make it clearer up to this point? And I'll stop sharing.
Sure. Don, I had just a couple of clarifying questions. Can you go ahead, with, Bucky and with Stroopy's work on this? We've looked at tetrahedrons, octahedrons, cube, icosahedrons, and dodecahedrons. One of the things that, Bucky mentions is that triangle is a stable shape, but square is not. When you put loops in it, are the cube and dodecahedron stable with the loops?
Give me the question again, please.
See, what happens is that when you make a tetrahedron, just with straws, just with straws just inside here like this, it is stable because each of the triangles is stable. But when you try to make a cube, it's kind of floppy because the square is not stable by itself. But when you put in these loops, does the cube become stable? Do you need to put anything to kind of hold, or is it held by itself? So that was
No,
one.
it's fairly stable. I have the Marana here. I just
Got it.
showed. There's flexibility here. It's not a rigid kind of structure,
Mhm.
simply because my materials are flexible. But when you're dealing with a particle, you're dealing with kinetic energy, not static forms of energy, and the strength of the form becomes very strong. And for instance, it's called the bonding energy. The bonding energy of an atom is in the millions of electron volts. The bonding energy of a particle is in the billions. And that Higgs electron, or that Higgs boson they're looking at, the bonding energy is in the trillions. So the more compact the form, the stronger it becomes. And the more deployed the form, the weaker the bonding energy becomes, until we arrive at us and we can't stand a volt of electricity. And we'll start deteriorating very quickly with 10 volts, you know. So what's happening is that I want to get into this, is when we go from atom to molecule, that's what is very interesting happens. And chemistry becomes the science that's going to be looking at that relationship. Is that any help?
Yeah, that's good. That's good. I think there are two more questions. Let's take more questions and then we will proceed. It's going to be DLJ followed by Joe. DLJ, go ahead.
Thank you very much. Is my sound working?
Yes.
Okay, lovely. Actually, it's not a question, it's an answer. You asked for any suggestions on how you could help to clarify. And this is an oversimplification from a simple person, so bear that in mind. But I just thought a problem statement at the beginning, which just says we have fields, we have form, but we don't know how to get from field to form until now. And this is where you say, look at what I've done. And I just thought that would make quite a nice intro, because it's the way I'm hearing what you said last time. And
yeah, you're right. That's what's so to me, what I really enjoy about working with this is finally getting a way to get energy and form together, so that I can understand that energy actually has pathways that it makes. I mean, we know this in electricity. We build circuits in our house and stuff, but particles and atoms build these circuits too. And, you know, while this form is linear, if this was a kinetic structure, what these lines are is simply the axis of the energy. And there's energy beyond this circle here, but this is the axis of that energy. So, you know, we can go from building this stuff with lines to building it with planes and volumes. And I played around a little bit with that, but it's a lot involved. There's what really needs to be done is to load these parameters into a computer animation program, so that we can really start dealing with it, because these things take time to make, and there's limited. Joe Clinton came up to, and we said, let's build the hydrogen atom completely, and it took us 4 days.
All right. Let me see.
And there's the tetrahedron in the center, and this is a hydrogen atom, and this outside tetrahedron is the electron field. But what's interesting is the electron goes through the nucleus, whereas physics didn't think that was possible. And they even invented something called normalization, which is a mathematics that prevents the electron from going into the nucleus, which it would want to do because of charge attraction, positive and negative want to get together. And they do get together, but physics couldn't find an example of that, because they thought the two would get together and explode. And And obviously that didn't happen. But there's a reason that happens, and I hope maybe to get to that sooner or later.
Let's take one more question and then let's continue. Joe, go ahead.
That normalization comment actually is very interesting. I'd like to come back to that. So just actually building off of what was just said. So if you're going from field to form, then currently physics is looking form to field, and that is preventing them from determining the momentum and the position of a particle. And so that's, I just want to make sure that I'm clear on that. So that's the idea behind the uncertainty principle, is that essentially you don't have a way of honing in on the forms. You just have, you're kind of looking out from the forms to the field. So it's like kind of the reverse, and that's what makes it impossible to predict where it's going to be.
Right. The image is the nucleus is still, and it's surrounded by this blithering motion of the electron that is external to that nucleus. And so they can identify where the nucleus, where the proton is, but not where the electron cloud is around it, as you suggest. Yeah.
Wonderful. Don, let's go ahead and finish up the presentation and then we'll open it up again for more questions and comments.
All right. We're about 2/3 through this introduction to Tometry, and I'm going to make it bigger so I can read it. So one thing that's important to note is that there are no fasteners needed to make this field structure. It's all done by torsion that is invested in the loops, trying to unfold in their various planes or axes. And if you build a form and you need a fastener to hold it together, and that includes everything we're building here on Earth, it means you're not using, you're still using what I call TNT, tetrahedrons and triangles, and to lock the form together. You know, all of our cubic architecture is only standing because we got tetrahedrons in this structure, keeping it rigid. So now, as far as I know, there is no other structural system that can enclose space without using fasteners. That this is the only one that can do that. So objects exist solely with torsion force, and that's made possible by knotting loops together. And these loops carry force, and the force is torsion. Twisting and bending needed to make a 3D form is the source of energy in the universe. The force being carried in the loops is the result of twisting. And I have a model here. The first presentation, I couldn't find this thing. Now I got it. I got to stop sharing here again. If we take a loop, and this string here is the same size as the loop, but I squeezed it together. But it obviously doesn't accomplish anything in terms of changing the loop. So what nature does is it squeezes it together like this. And notice that the loop bends into a shape because of the way the loop has been pulled in from both sides. And this is the makings of the nucleus. If I add 3 more of these, then I have a structure with a condensed energy all in the loop, all in the nucleus. And here's the model. This is three of these. And that gives you the structural loop. And notice that these loops in the rope were originally around the loops that were in, in this shape. But when I condensed them and in this form, all three of them, notice that all the frequency of this form is sequestered to the nucleus. And this is what we find in an atom. 94% of the energy of a system, of an atom, is in the nucleus. And the energy that's still out here deployed only has 1 unit per loop. So 0.06% of the energy of an atom is in the field. The rest is in the nucleus. And that's the difference between an atomic bomb and a hydrogen bomb. The atomic bomb is dealing with this external 0.06% of the energy. A hydrogen bomb is dealing with this nucleus, which is extremely more energetic. So now we have a way of modeling how energy gets sequestered into the nucleus and still have a field around it. And the model I showed there was if I took this knot, this loop that has been looped together, actually I better use this one. This is 2 loops woven together. And if I hold this and squeeze this down, like I'm doing, I end up with this form. All of the energy comes to this point here, and I have this field out here with only 1 twist in it. And by drawing a line on this rope, I can count the number of twists that things have. So what this structure here is doing is taking all that energy to the nucleus and keeping it there. And it keeps it there through electrodynamics, through, that's a whole nother discussion, which is really beautiful, but that's what happens. So now we have a way of accounting for electromagnetic energy, which comes in the form of a wave. And in this case, all waves are circular, but this is a very small one. Most light waves are huge structures. And when we condense this energy into a nucleus, which the universe is doing all the time in stars, the function of a star, I'm jumping around here, but the function of a star is to take energy and create matter. And the matter it creates is hydrogen. That's why stars are 80% hydrogen and 20% helium. We've got a model for how this now works. So back to the paper. Okay, so to create the structure, which is this form here, it is necessary to create a nucleus, and the energy field that goes around and through the nucleus is necessary. So what we have in the in this form here is that we've taken the other wave that was in here and sequestered it to that nucleus. And now now we have a way of looking at what energy is. And I'm going to stop sharing again. This form here has taken the frequency of this wave and sequestered it to the center. But as a single wave, there's nothing to prevent this from just redeploying again back over the loop into this form. And so nature hasn't finished its job. It needs to have the other two waves interacting with it to bring them all together and form a polyhedral nucleus. And then we have a situation where we've sequestered energy, and now we can redeploy that energy if we break the knots that are holding it from being free to expand. So energy is this form here has potential energy, but it doesn't have kinetic energy because the loops are evenly deployed throughout the form. There's no any asymmetry here. But when I do this, I create asymmetry. I create a block of energy down here and none up here, and it wants to redeploy. So any form of energy is the redeployment of mass to the radiant state of this ultimately. So this is what entropy looks like. And this is what centropy looks like, or in this model here. So this is centropy. This is nature's way of giving us a universe that will endure in time. And when a situation occurs that we can break these knots and energy is free to flee, then we are returning energy back to the plenum from which it came. And that is what entropy is all about. Now back to the screen. So I've explained all of this so far in the book that I just showed you, the particle hierarchy paradigm. So now let's look at the higher orders of structure. While having a model for a particle structure may be an achievement, but there's still forms more complicated than particles that field structure theory must explain if it's to be comprehensive. Tometry needs to explain the structure of not only atoms, but molecules right on up to the forms of the universe itself. So I've already shown you the structure, which is the template for particles. The template for atoms is the superstructure, and that is this form. Here we can see the nucleus, tetrahedron, and the tetrahedron in the electron cloud field. And so that is the model for atoms, the superstructure, polyhedra inside of polyhedra. And I've built other models where I go for different shells. Like this will be the first shell of an atom, but atoms have 6 shells. And when you're dealing with the 81st particle, you are dealing with 6 different shells that have a total of 81 loop structures comprised in it. Now, this model of an atom is only showing one handedness of the loop. And here we can see the handedness is going clockwise. But because the loops are made out of electromagnetic energy, which is right and left-handed energy in the same form, which I showed that circular loop that had the 2 forms looped together, we need to put the other loop into this structure to get the full picture of what an atom is. And this is the same atom. This is also a tetrahedron, but because I've got a right and left-handed tetrahedrons in there, it takes on a cubic form. And that's important because cubes close pack and tetrahedrons don't. But nature is able to close pack any form because it has both, it can do it with applying both clockwise and counterclockwise rotations of itself into the same form. So this is called a double cube superstructure, and is a true representation of what a simple hydrogen atom would look like. And it is this form here with both right and left-handed circuits in it. And that's one view. And now here's one that has 3 different circuits. Right in the center here is one tetrahedron, the little one. Then we have another one that's around it. And then we have a bigger one yet that's around that. And this is how nature builds complexity in a form, and why we can have 81 different elements is because we can keep building these forms and adding shells, and each shell is an electron, is the path of electron structure in that form. What is also important is that, like the structure, the superstructure has only 3 right-handed loops that are doing the work of 6 that would need if these electron structures were and the proton structure were separated. So you see, as we build, we simplify. We use less energy than if the 2 forms are separated. The combined form needs less energy. That's why in any combination, there's always heat is always given off. And what that is giving away loops that don't need to be there in the new structure. So the problem physics has had is that the field energy can't be seen. And this is an obvious observation that I think goes completely misunderstood. There is no idea where the electron goes and what the circuitry may be. Physics presently only knows energy by how it affects the nucleus. And that's been a problem. Now let's move to the molecular platform. We've discussed what a particle looks like, how that Tometry can morph into an atomic structure. So how does it work with a molecular structure? And the first presentation I made, I said something that was wrong. I showed, and I'm going to go back again and stop sharing. I showed this structure. And what you see is 2 tetrahedrons joined by a loop. Well, actually 3 loops in this form. And I misquoted and said it was only 1 loop, but I picked up the wrong one. This one here has only 1 loop doing all the work of joining the 2 tetrahedrons. Now, why is that? I mean, why is this one, which looks exactly the same as this one, why does this one require 3 loops and this 1 loop? And the answer turns out to be the number of times it's twisted here in the joining section. This has 1 twist, and this one has 3. So, I'm sorry, 2. This has 2. Odd numbers need more loops than, odd numbers need more loops than even numbers, which is That is really something to think about. And so what we have here is really a diagram of what's called a valence electron. And valence electrons are the electron that goes from one atom to another one. And in hydrogen, which only has one electron, it joins another hydrogen to make H2 it can join with one electron, or it will need three to do that. So it obviously prefers to do it with less energy, which is only using one loop. I've built other examples. This is 3 tetrahedrons, which are the stick figures here, joined with one loop. Now, if each tetrahedron were separated and made into its simple form like this, the number of twists and loops change when it joins up with other atoms or other atoms. And so nature is finding a way to do more with less. And this is a vivid example of how that works. So now we have a way of explaining that molecules are sharing electron energy. And we can define that structure by the number of twists that are in the form. This could be a whole nother thesis. So I'll just want to show you that the structural system of field structures can account for particles, atoms, and molecules. I haven't even gone into cells yet. I built some models that have maybe 50 different tetrahedrons in it, but it's just overwhelming to get beyond that. This is where the computer guys really need to settle in and work out all the connections. Now, all we need to know here is that it can be done. So let's go back. Stop sharing. Oh, I am going to share. Share screen. There we go. Okay. So I won't go into all these details, but Shrikant, can people download this paper here?
What you can do is you can go ahead and email it to me. And
okay.
You know what? Yeah, you go ahead and email it to me, and I will, you can email it sometime during this presentation, and I will go ahead and put it in the chat so people can share it, people can see it.
Okay, all right. Once I get through it and build and go into building a model, I'll send it to you. Or would you rather do it later?
No, that's fine. I think it's better to do it while we are doing the model, even if it means a little bit of interruption, because people would like to have it.
Yeah. Okay. So, with Tometry, as I mentioned before, position and momentum can be known at the same time by knowing how many loops are involved in the form and the number of twists those loops take to make that form. And all of that is encoded in the polyhedra itself. So if you have the polyhedra, you know how many loops and how many twists are in the form. And this needs to be put into a chart sometime. So how is it known? By knowing the polyhedra nucleus, the number of loops and twists it takes to make the form can be calculated. Momentum, and which is energy, is a count of the twist. Position is determined by the number of loop interactions, and there are in the form. The fact there are multiple places the field particle the electron, can be found in an atom leads to the conclusion of the multiple certainty principle. And this, I see this as a more exact way of understanding the certainty of an atom. Physics right now has the uncertainty principle, saying you can't know those things, but with field structures you can. But the twist is, so to speak, is that where something is in a multiple different places depending on the polyhedra nucleus of the event. So the electron, the tetrahedron, if you know the particles of tetrahedron, you know there are 4 places you can find that electron and exactly where they are. And if it's a cube, you know there's 8 places. And an icosahedron, you know there's 20. So whatever the polyhedra is, however vast, how many millions of faces it may have, there is always a multiple certainty of finding the particle that's sustaining that field in a certain number of places. So while the uncertainty principle has to deal with everything in terms of probabilities, Tometry deals with the geometry of particles as a set number of places it can be. Here I'm showing the molecule again and how it's sharing these loops. These are other molecules. This one has 4. There's one behind this one in the middle. And here's one that has 1, 2, 3, 4, 5, has 6 tetrahedrons linked together. By the way, that's benzene right there. The valence electrons of benzene. So I've talked about the valence electron and how that works and how energy shares. So here I'm going back and doing some loop studies, and let's see, yeah. So if I'm sending you this paper, you can go back and read these particular things. So applying what we've just learned to wave entangles in 3D structures, previously shown was the single loop, and we put both loops in, and this is called the ambistructure with right and left-handed loopage. And this form here, actually, though I can build it, in nature, this form would immediately, if it was built like this, it would immediately morph into a different figuration. The one of the, let's see, do I have a picture of it? No, okay, I'm at the end here. This field morphs into what happens is the white loops are over top of the blue loops at this joint here, at this vertex or vortex. And that means the white loops are cloaking the blue loops. And this is something that I want to get into. The question is, why do waves wave? Now, I've never read anywhere in all the books on physics I've ever read is an answer to that question. Why waves wave? They know they wave, and it's such a common thing that is not even questioned. It does wave, but why? And the answer that field structure theory is telling me is that because you have right and left-handedness in electromagnetics, when one is what I call an anti-wave and the other is the real wave, and the real wave rotates counterclockwise. So the electron rotates counterclockwise. The positron, which is its dual, it's a chiral relationship, rotates clockwise, left-handed. When the real wave, which is counterclockwise, is over top of the anti-wave, in this case, the anti-wave is blue and the real wave is white, it cloaks from view the wave that is behind it or over it, or under it rather. So a wave waves because the anti-wave is obscuring the real wave. So if you take a rope, and let me go back to stop sharing. If you take this loop wave, and as you can see, I've marked them with black lines and red lines. You can see a bit of a red line coming there. So they're wrapped around each other. And one of these is going clockwise and one is going counterclockwise. But you can't tell which is which until you compress the wave. And what this does is take all of one-handedness and squeezes it down. So this one down here is rotating clockwise. This one up here is only rotating counterclockwise. And now you can see which wave is rotating one way or the other way, whereas in this form, you can't tell. So that's why light, we can't tell if it's right-handed or left-handed because it's both-handed. But we can tell that it's going on because light pulsates. It goes from a high amplitude to zero amplitude and back again billions of times a second. And that flipping back and forth is because the loops are overlapping each other. When this loop is in front, you can't see the one in back. And so it really comes into an issue of the fact that we as real matter, real wave people, we can't see antimatter and antiwaves, but they're there. They have to be there to explain why waves wave. And here's one of the top 10 problems in physics is what happened to the antimatter? They know that it has to be made whenever you take energy and make real matter, you have to make antimatter at the same time. This is a known fact. And but still everyone is looking around and saying, well, where's the antimatter? The fact is the antimatter is entangled with the real matter so that the wave pulsates, proves that there's the antimatter there. It's just that we can't see antimatter. Actually, we can see antimatter, but that's another story. That gets us into metaphysics and yoga. So the issue of what happened to matter, one of the top 10 problems in physics is that matter is right here with us. All that antimatter that had to be created is not lost. It's just not visible. And furthermore, we can't see light. We can't see this wave running across. If you look around your room and all, there is light waves going every which way without us being able to see anything unless it hits mass. And the mass vibrates because it's been hit by this light. And if that mass doesn't need that frequency, it bounces it right back. And thus we see something, but we don't see what happens between the start state and the end state. And that's where this world of energy lives, in there. And we're just these little isolated stopping points that energy makes in its course through the universe. All right, so maybe at this point it's time to build a structure. What do you think?
Yes, yes. Let us go ahead and build a structure, and then folks, keep your questions. Because it's just wonderful. I've been working with all of these things. It's just amazing. So I want everybody to be able to play with this, so you can actually see how it is actually put together and how the tension works. So Don, please take it away.
Okay. The tools are simple. Your hardware store has all the tools you need to model atoms and molecules and the rest of it. You don't need $1 billion cyclotron to do this.
All right, Don has just saved you $1 billion, folks.
Now, what did I do with my rubber bands? Hold on. You need 3 things. I use 1/8" dowel rods. If you can find them in maple, it's better, because there really gets to be a lot of force in this stuff, and it'll snap one of these sticks if it's particularly big. That hydrogen model I showed you is just crumbling apart because the energy is twisted it all around. Okay, so we start with sticks, 2 sticks with different colors. 2 blue, 2 red, and 2 white. So the first step is to take one of each, red, white, and blue, and just put them together. Screen goes backwards. And we'll take a little rubber band and we'll put around one end of it, put it around twice. There we are. We got that. Red, white, and blue. Now we take one of the sticks, and I took the red one, and I put the blue and the yellow with that one together and put the rubber band on them. So that leaves us with 1 stick left. And we spread these apart. We find a red, yellow.
Don, can I request one thing?
Sure.
Can you move the camera further away from you so people can see? It's like it's going in and out. Sit a little bit further back. Yeah, much better. Much better.
Okay, so now I've taken where I had 3 of them put together. I take 2 sticks and put the 3rd one up there. And now you have to be concerned about how these sticks are rotating around each other. And you can do it right-handed or left-handed here. So I'm going to do a counterclockwise connection. And I'll get it together and show you what that looks like. Okay, so now I've got three sticks together here, and I've got 3 sticks together down here. So now I got to put together the remaining 3 in the counterclockwise position. They've all got these sticks all have to be rotating the same way. If you get mixed up and put right-handed in all places, and the left-handed one there, it's not going to work. So in a way, what I like is the forms are self-proofing. If you don't get it right, they collapse. That's convenient. So now I've got everybody banded together. And, you know, leave that.
Don, can you show people, because this is where I had screwed up when I was first trying to make it. Can you explain to people the right-handedness, just show them how each of them is going just one way?
Yeah, okay. All right, let's start with this one. This is rotating clockwise. Can you see how that
Yes.
is?
Yes, it is. Yes. Yep.
The screen is reversing my hands.
Yeah. Don't worry about it. We are seeing it right. It's just
All I need to do is to make sure they all have this kind of rotation.
Yeah. Can you
Let's
show
rotate
another,
this and see.
another option? If you could bring it in. Yeah, there. All right.
This one is rotated wrong. This is not right. So I move the sticks around.
Folks, this is very important, because if you don't get this right, it doesn't stay. I've tried it. I've struggled with it. So
Yeah, just take a look at what's going on at these vortexes and try to get them spinning all that same way. Like think of it as this is the way you model. This is left-handed, but on the screen it's right-handed. The screen is reversing me. This is really tricky. So right and left-handed. And so think of these three sticks.
okay, Don, let me help you. You know, you see the video icon at the left bottom of your screen in Zoom. There is an up arrow. If you could hit that up arrow.
Where it says whiteboards?
No, where it says stop video, right next to it, there is an up arrow. So hit up arrow.
Oh, there. Okay.
Select video settings.
I hit the little arrow beside stop screen.
Yes, stop video.
And I get one participant can share at the same time.
No, not stop screen. At the bottom left, there is a mute, and then there is stop video.
Right.
Stop video. So hit the up arrow right next to the stop video and click on video settings.
Click. All right, I did.
And there it says mirror my video. There is
All right, now shall I go back?
so have you clicked on mirror my video?
Yeah, I clicked on that.
Very good. Okay, so now go back. Now I think it should be fine.
Okay.
Can you start your video again?
Can you see me?
No, you have to start your video.
I need to close out of stop sharing.
You can just go ahead and click on, I've asked you to start the video. You can just say, okay.
Let me get rid of this. Okay. Oh, wait a minute. Now I've blocked myself.
Yeah, you can just go ahead.
There
Yeah,
you go.
there you are. Now, is it looking better now? Is it fixed now for you?
Let's see. All right, that's going. That is rotating clockwise.
Okay.
That's right. Okay, we got it.
Okay, very good.
Okay, so we just take a look at all of these and see if they're rotating. That one's okay. This one isn't. Can you see this one is rotating clockwise?
Mhm.
Now, let me see. So you have to switch them around. Okay. All right. All right. All right. All right. Okay, now we've got this form. We're ready to apply the loops. So on the blue stick, we insert our blue tube, and I'm going to do one vortex first. Here's the red one. And the yellow one. Okay, got a little plant going here. Now it becomes important which way you bend this loop to connect to the other red stick. And so looking at the vortex, you want the loop to cross over and make sure it's crossing over. Oops. Is it tricky? All right, I got that backwards.
Don, can you move your video a little bit down so it is always pointed to what your hands are doing so
Yeah,
people can see it? Yeah.
it'd be good to have someone else to handle the video. Okay, there we go. So we're taking this red one. We're gonna cross over the blue one and connect it. There's a lot of force in that. It keeps busting apart. And you might want to put a whole bunch of rubber bands if it gets too squirrely. So we do the same thing with blue, crossing over yellow. And yellow crossing over red. Whoop, came apart.
See, basically the entire structure is held together by tension, and the material that Don is using, it's quite stiff. The tubes are very stiff, so they produce tremendous amount of tension. So it is quite a feat.
This thing is just falling apart right and left. I should have put on more rubber bands. I'm going to have to go back and re-rubber band this thing so it
Sure.
runs apart.
Sure. So folks, let me, while Don is doing that, let me show you. I have another version of it, which is just, I'm using tubes, so there isn't that much tension. I've just reduced the tension because I had all kinds of problems of things falling apart. The beautiful thing is that once you actually build it, then it stands by itself. So firstly, I want to show you what the rotation looks like. You see, this red is on the top of blue, red is on the top of blue, and then it is blue is on the top of green. So you have to make sure that the same pattern is there. Red is on the top of blue, and then green. Same like that for each of this. So that's the rotation of these parts themselves. Okay, there's so you can see that each of them, red, blue, green, like that. Red, blue, green for this one. Red, blue, green for this one. And red, blue, and green for that one. So that's the idea of making sure that it is rotating, all of the tetrahedron is rotating the right way. And now we have to make sure that when you put the tubes in, they are also rotating consistent with that. And that's what produces those interlocking torques, interlocking tensions that hold everything together. So initially you have to use these strings or rubber bands to hold it together, but once you have put it together, it stays by itself. It stays by itself just by tension.
That's very good. Very good, Shrikant.
Well, I've struggled enough with it, and Don, you have been great help. So I'm just returning the flavor by passing it on here.
Yeah. I'm putting 3 or 4 rubber bands on these things so they hold together, because as Shrikant mentioned, these tubes, it's amazing amount of force those things exert.
So
And
I had to go to the hardware store and choose these tubes which can take a little less tension. And somehow they still work, because they are, instead of holding to the edge here, they are now holding, they're kind of placed inside. So it uses the leverage of the tube in order to keep the structure in.
good.
I have to only figure out, I have to take help of Jeannie to color these things right, because what I have done is that I have cheated by putting these faint, you can see the faint red here. I've tried to put red strings in there to kind of show that this is red, but that's not ideal. So I have to figure out how to color it up nicely.
All right, this time I'm doing one loop.
Okay, so
And
folks, if you look at the one loop, right?
it'll be easier that way.
Yeah. So can you show the one loop what it looks like? Because that's a really core idea, because this is the, yes. So you can see, folks, that it is like an infinity sign, but if there is the two crossing bars are at right angle to each other. So there is a 90-degree turn like that.
I would have less torque in this if I use longer loops.
Yes.
These are short, so they're really hard, twisting hard. Now blue. The thing to be sure, to be like, when you look at this vortex here, just make sure the blue loop is going over top of the stick that it's next to. If you went this way, it wouldn't be over top of it. So that's where you get this locking going on. So now
And ultimately what you want to get is something like this, a spiral like that, where everything is going in the same direction.
right. All right. This is the final blue one. Now we're getting somewhere with this. And all we got to do now is finish the yellow one. So my first attempt showed the wrong way to do it, is to try to do it all from one vortex. It's just choose one color and get that one going. And now we've got our structure the way we want it. And at this point, I can cut loop, check to make sure each vortex is spinning the right way before you cut away the rubber bands. Okay, it's right. So the proof of the matter is when you cut it, does it fall apart? There's one. I got about 4 or 5 rubber bands on each one. There you go. And one more. Okay, there it is. No fasteners. And we got a three-dimensional form. With the tetrahedrons is easy. When you do cubes and dodecahedron and all, you got to get pretty fancy with holding everything while you're sticking it all together. And with those, I build a three-dimensional form, solid, and stick the sticks on the edges with tape and glue, and then try to put it together. Doing it this way with more complex forms is just too much to handle. You got to build the solid form to work with. So that's how we began building this stuff, and this first two programs were done in order to describe the tometry, or the geometry of what it's all about. And I've talked about somewhat about how you apply this to natural forms and structures, particularly in fundamental forms, particles and atoms.
So Don, let's give a chance for people to ask questions. First,
Yeah.
If you have any questions about building structures, because I strongly recommend that you do that, because that's the only way to actually grasp, working with your hands. At least, I mean, that's how my mind works. So I need to do that. So please go ahead and ask any questions that you have. First, about building of structures, if you have any questions or any comments. Tanya is planning to build a roller coaster ride along each of these things that are intercrossing each other. So that's very interesting. All right, folks, questions about this, or you can now ask questions either about, let's start with DLG. DLG, go ahead.
Thank you. Yes, so not so much the building, I suppose it's connected to. I'm sorry if I missed this. It's a lot to take in. When I asked my previous question, you said you have to imagine the loop as the axis to the field, yes? The field's axis. If I got that right, then I don't get how, and again, sorry if I missed it, I don't get how how does the twist in the field, you had those twists? So how does the twist in the field happen? I mean, in reality, not in the model. And what causes a twist in the field?
Well,
Thanks.
Michael Faraday, who discovered fields, showed that nature does this twisting, and the whole basis of electrical motors and generators exhibit the necessity to wrap and twist. Wrap and twist is kind of the same idea, around a form, actually bend space. And the thing where you put a magnet under a piece of paper and sprinkle iron filings, you can see what the field looks like in one plane. But imagine that as a three-dimensional form, and what you're getting is one of these forms. And so the twist is the secret to unlocking our relationship to space. Mass and energy is related to space and energy through twisting. And in this book here, I explain how that works, and you can see. Show you some things here. Here's an example I really like. Let's see if we can see that. I took a sheet of shim steel and just let it hang, and there's no tension on it, and it's just a straight plane. And in the middle one, I started twisting it, but not putting any tension on it. And in the third one, I pulled on it and twist, and look what happened. It broke into 45-degree, 90 triangles. And the more that this is one complete rotation. And there's something like 10 different 4590 isosceles triangles in there. As soon as I tried to go beyond, twist it beyond that, the whole thing exploded. The metal just tore itself apart. But as you twist it, you are condensing space. That sheet of metal got shorter. The more I twisted it, the shorter it got. And waves work this way. A high frequency, high energy wave has a lot of twist in it. And radio waves have very slow, gentle twist. What it's doing is following the structure of space. And the structure of space is like all possibilities, but the amount of twist of a loop will determine which of those possibilities is going to be chosen, and it will break out into a geometry. So space, once you apply twist, becomes a tensional network. And this is what tensegrities and particularly are showing is how that works.
So if I can quickly follow up, when you say once you apply twist, what's the in the universe, what's the you that's applying twist? I know it's not a you, but where does it come from? How does the twist happen?
That is good. That is a deep question. And
okay, that's your homework then.
Following that one, I have to go back to, well, where is this all coming from? What is being twisted? And the answer to that is, it used to be called ether. I call it plenum. In Sanskrit, it's called akasha. You know, what's interesting here is that the Vedic sages have already mapped all this out. I'm just repeating more or less what they have said. So from this everything that is the plenum, what could possibly act on the plenum to create a tension in it and break up into the geometry of space? And the only thing I can come up with is consciousness, because I don't see a difference between this plenum, which everything comes from, is any different from the concept of consciousness. And I think the first presentation I mentioned a beautiful example of how a seeming nothing can create enormous effects. And consciousness is a seeming nothing that can create enormous effects. Words we've developed can move nations, build rockets, do all kinds of stuff. And so something, you can go online, look at this, it's really cute. A tiny little rectangle that big was set down, and behind it one a little bit bigger, and then a little bit bigger behind it, until at the end of this progression was a 1-ton block cube. And just with a feather, the first tiny little cube was knocked, and it fell over and hit the next one. That one fell over, and that one fell over. And in the end, the ton rock or cube goes falling down as well. So we have examples of what small effects can produce tremendous results. And the smallest effect I can think of is consciousness working with that plenum to create a cascade of events that ends up producing the names and forms of our universe. Because each fall is a twist, in a sense. I kind of like that image.
Go ahead. I mean, I'll approach it another way. I mean, you kind of have to start by looking at patterns in nature, what are there. So for example, you can say, okay, what makes the spirals in the ferns? What makes spirals in the in the shells. And so there is something about it, and you're kind of looking at patterns in nature and you're trying to capture it with geometry. So it goes from, you're always trying to go from kind of what you see in nature from to theories. So thank you, DLJ. Folks, now you're open for questions on anything about what has been said. So next up is Joe. And last time Mike didn't get to ask the question, so it'll be Joe followed by Mike. Joe.
Thank you, Don, actually for doing the presentation. And I mean, this has been mind-bending, literally. So one of the things that, obviously that Bucky does with synergetics is he relates it to a number of different fields. And you started to just do that right now. And one of the things that I looked up maybe as a possibility is how to think about field theory was dropping a pebble in a pool and how it actually impacts the boats if they're floating in that pool. And so that then you start to, so this could be applied to something like psychology in the sense that how your environment shapes your understanding of the world. So these events that are created. But then you said something interesting. You said we don't see the start state or the end state. And I wasn't clear on what you meant by that.
We don't see the start and end state. We don't see what goes on in between.
Okay. All right. Then that actually clears it up for me, because that would be an experience, right? It is like a start and an end state. So that you could actually think about that's an event that actually triggers other events around it. Okay. All right. Well, so that helps me understand. Okay. And then how everything is interconnected. Okay. All right. That helps me grasp this a little bit better.
The thing that's missing, I think, in physics is by not knowing how what happens between start and end state means they don't understand that has structure, that the energy that's going from one place to another is carrying with it structure, and it encounters the end state, it delivers that structure to it, and that end state then morphs to accommodate that structure. But there was structure in that energy that was flowing across. And I don't think that's appreciated the way it should be, because it's never been able to be modeled.
Oh, you're muted, Shrikant.
Thanks. Thanks, Joe. Thanks, Don. Don, let me ask you a quick question. Can you explain why you have the Sierpinski triangle on the cover of your book?
Well, after discovering the structure and coming to the conclusion that with these loops, I can make any form in the universe, then I should be able to go to physics, who has discovered the energy it takes to make these particles and what their energy values are. And I should be able to replicate those relationships in these structures. And if I can't, it doesn't apply to the physical universe. It's just an abstraction. So then when I started taking the simplest organization of 3 loops to make that tetrahedron, I organized them as, and I'm not sure why I chose the Sierpinski triangle fractal, but I started with putting one triangle of the Sierpinski triangle at the top, and I thought, well, okay, those are the three loops. Let's let those 3 lines equal the 3 loops. And then I said, well, now let's add another set of 3 and another set of 3. And I found that from that tiny little loop at the top, I put 3 around it, joined at the vortice. And then around that, built another set equal to the one I had previously made, because this is a fractal. And when you add fractals, and when I got to 7 iterations of this fractal, let me show you the picture in the book. Can you see there are 7 iterations there from top to bottom? The notations on the side are the number of loops up to that point.
Yep.
Those numbers match exactly particles, the number of electrons in let's see how to put this. If back when in the days when mass values were calculated in terms of electron masses, you don't see this much anymore because now they use electron volts. But they noted that the proton, for instance, it took 1,836.157 electron masses to make the proton. And what the Sierpinski triangle fractal did was all of those iterations are the number of electron masses that equal that particular particle. And they're all falling out. This book describes all the combinations of those things to show you which particle needs so many of these basic loops. And the fact that all those numbers are there just blew my mind. And interestingly, this happened the day before the new millennium, December the 31st, 2099. And so the Sierpinski fractal is a diagram. It's not a structure in the sense of a field structure, but it's a way to diagram the how action accumulates, and it accumulates in this fractal manner. And if I did 7 iterations here to get to the bottom, which had 2,187 loops in it. That is the mass of the lambda particle. And a lambda particle is more massive than a proton. And I thought, well, gee, you know, why doesn't it end with the proton? Because that's the next stable particle up from the electron. And but the proton only has 1,836 loops, whereas the lambda, the 7th iteration of this, has 2187. That's when things got interesting, because let me see if I can find that photo. Yeah. Here we see I've taken away a certain number of the loops in that triangle. So I've got 2 at the bottom, which are the same, and then another set at the top. It turns out that in quantum physics, the standard model, the proton is made of quarks, 3 quarks. And here are 3 quarks. And 2 of them have the same energy, and 1 has a third of what one of the 2 has. And that is what I just showed you, that picture. The 2 bottom ones are called up quarks, and the one that's only a third as strong as one of those is called a down quark. And so here we've got a structural way to explain the whole quark theory. And to me, that's really great, to be able to model what's going on, and instead of just measuring the energy of particles in a laboratory without knowing what the structure was, you can make a description. And that's what physics is really good at, describing things. But it's very poor at explaining things because it doesn't have a structure theory. And that's what I want to supply, and hope the physics community will be able to use it.
Wonderful, thank you. Let's go with Jeannie next, because Jeannie is familiar with Tom's work. Jeannie, go ahead. And Joe, can you handle the moderating for the next few minutes? Okay, thank you. Jeannie, go ahead.
So, Don, in real life, I guess, there are no perfect polyhedra. And, you talked about the bonding, and it's so much stronger at the smaller scales. Now, would that possibly mean that at smaller scales, polyhedras tend to be more perfect or regular than at a larger scale? Or does, the fact that it's smaller, counteract that, and then the resolution would be maybe the same for large and small objects? So just wondering what your opinion is on that. Of course, none of us really know, but
that's a good question. And it in a wave, you can have, say, 3 nodes in a foot, let's just arbitrarily say. But if you squeeze that together, you have 3 nodes in 1 inch. And frequency, the power of a frequency depends on how many nodes in a period of time it has. So in the period of time of 1 foot, the frequency is low. But if you squeeze the time, you squeeze the wave, now you got 3 waves occurring in half a second instead of a minute. So it becomes much stronger. And as particles condense and get smaller and smaller, back to this again, this is the electron model. But what is going on inside of this loop? This is the neutrino in here. So while this central part is the electron, which we work with all the time, we're unaware of this neutron or neutrino structure that's going around being its field particle. Just the way an electron is the field particle of an atom, a neutrino is the field particle of an electron, and it goes down because now we're back to fractals. So the smaller it gets, the more concentrated that wave becomes, and that's why it has more energy. It's squeezed into a smaller, but you can take that same squeeze and reposition it into a larger wave structure, and the energy comes down, but you got more space. So there's a relationship between energy and space, that if you want more space, then you use energy to get it. And if you want more energy, you squeeze that space.
Wonderful, thank you. Next up is going to be Mike, followed by Will. Mike, I'll give you 1 minute. If just let's try to keep it on the topic, please.
Okay, I don't quite understand what's going on. Have you used the shell approach, which we know is wrong? You can do calculations of, for example,
Mike, just go ahead and ask a question, please.
that's the question. How do you reconcile this with the shell approach? And how do you compute barrier potentials? Can you map this into the shell approach, or can you map it into Feynman diagrams? Because you want to find, typically when you want to find something, you want to find barrier potentials or tunneling probabilities or particle decays. How do you do that kind of calculation in this paradigm? I know how to do it in the shell approach. I sort of know how to do it with the WKB approach or Feynman diagrams, but you don't always get an answer that matches empirically.
Thank you, Mike. Go ahead, Don.
Mike, I didn't quite understand what your question was. And it's partly because I can't hear you quite well. And I apologize that I have hearing aids and they're not so good sometimes in certain things. So
Sure. Let's do one thing. Mike, can you type that question in the chat and I will read it out for Don. Meanwhile, let's go to Will. Will, go ahead.
Thanks, Shrikant. Excuse me. Thanks, Don. So fascinating. This is a general question, so physics related, but not specific to this topic. So I don't, at risk of upsetting Shrikant, I just wanted to ask you, do you believe we can ever come up with an answer, considering that energy existed infinitely without first cause, or alternatively, it emerged from a pure, utter, pristine void? So they're the only two options we have available to human logic. And some people get upset when I ask this question and they say, we can work it out. Which fascinates me, that people do tend to get upset, some people, when you say, I don't think we can ever understand something without cause. I just want to take the opportunity to ask you.
You know, I'm always looking for that cause too. And chasing it down, like I mentioned earlier, like why do waves wave? And I explained how that worked, you know, and then the conversation zeroed in even further. Well, what's waving the wave? You know, what's causing this energy to vibrate as it's such? And I mentioned I had to go all the way back to the issue of consciousness and how consciousness interacts with the stuff of the universe. And this, I hope I'm dealing with your question here, but in Vedic science, reality has two aspects. There's consciousness and there's the stuff consciousness works with, and they are actually the same stuff. It's called Prakriti is consciousness in Sanskrit, and is the stuff, and Purusha is consciousness, and they're inseparable in a functional sense. But I kind of look at it as like a hurricane. You have a still eye center, and I've been in the center of a hurricane, passed over my town. And after the wind just was tearing everything apart, the eye of the hurricane came over the town, and it was dead quiet. And there was no wind or anything. Yet where the eye of the hurricane goes, the storm goes. So the storm's got all the fury, but it can't do anything without this eye moving.
Yeah.
So I see the relationship between cause and effect, yeah, as that kind of relationship, that the cause is the still center and the effect is all that's going around it. But it's the still center that moves, and that still center, it could only be, in my terms, consciousness. Is that close to what you asked?
Well, yeah, and I apologize, it's a bit of a question without notice, but I don't think we can ever come up with a solution. You know, it's forever beyond human logic, because everything has cause and effect, except that something existed without cause, it just was, or it came from nothing. Just all the energy in the known universe came from nowhere. So I think it's forever beyond human comprehension. I find great sustenance in that, in knowing that we live in a reality that is literally beyond anyone's comprehension. So that gives me meaning.
Yeah, you certainly have a good point there. that was a question that haunted me as well. And I really had to go and study with sages that have been working with this their whole life. And the answers they come up with really sounded right to me. And when I first went there and asked that kind of question, why is it you sages sit here and do your meditation and you do some work in society, but basically you seem to be very remote from it all. And the answer I got really impressed me. It was, why spend your time with trivialities? We've only got 30 or 40 effective years to figure this out if we're interested. And if we're involved in trivialities of all the cause and effect mechanisms, that we'll never get to the point of encountering the absolute. And once you encounter the absolute, those cause and effect questions, they get in a way answered by not answering them. And I find that about the only way to deal with it, to deal with those questions.
Thank you. Let me go ahead and read out Mike's question. Mike has typed it in the chat. It says, how do you reconcile Tometry with shell approach? Or how do you use Tometry to compute things like tunneling probabilities or barrier potentials?
How do I use Tometry to do what now?
Shell approach, or
Shell?
or computing tunneling probabilities.
You mean like atom shells? Shells of an atom?
Yes.
Yeah. Well, I guess I would go back to the Sierpinski fractal there to figure that out. Knowing the basic form, which is the topmost little triangle there, as I add loops to the structure, they are going to reach levels of compactness that demand the energy goes to a higher level. Like you can only do so much in the first shell. It can only handle 2 electrons. So if you want to put a third one in, you can't put it in the same shell. You got to start building another shell. And this all has to be worked out in the relationship between the polyhedra, the number of faces and edges and vertices that it has. You have to work out what the loopage is going to be in order to produce that form. So if you have a form that's, say, at this level right here, this iteration here, that form happens to have 81 triangles in it, 81 loops. And there are only 81 natural elements. And those loops are electrons. So this fractal is telling me that after 81, if I want to add another electron, it's not going to stick. It's going to have so much energy, it's going to fly off. So the energy of a beta electron, which is a radiant electron, no longer can be bound to a mass because it's got too much energy. So you can build this. There's 6 shells possible, but at the 7th shell, it's just too much energy and it just flies off.
Wonderful. All right, Tom, I promised you that we'll keep it, close to 2 hours. So thank you so much.
Yeah.
And thank you for jumping in the middle of what you're doing with your family. So really appreciate that.
I'm
And-
sorry about that, Shrikant.
No problem at all. No problem at all. So any kind of what did you get from the meetups? If anybody wants to just give comments about what they got from the meetups, please go ahead and type in exclamation mark. Just very brief comments. Go ahead.
I would like to add that if there's any interest in this, I would like to go through this book and explain deeper how I'm getting this into actual physics. And Tometry is the geometry, but to apply it to physics remains rigor that is a separate issue. And I'd be happy to go over that with anybody that wanted to hear it. Okay.
Wonderful.
And I apologize for being late. It's just
Oh,
terrible.
no problem at all. Joe, can you do me a favor? Can you go to Amazon and find a link for Don's book and put it in the chat while other people are giving comments? Thank you. DLJ, what did you think of the meetup?
Oh, as with last time, yes, I'm in awe. Very impressed. Thank you. Except I got to say that I felt like there was a consciousness of the gaps argument. So they're saying, therefore, I think that's a category error. But other than that, yeah, it's delightful. Thank you very much.
Okay, wonderful. Thank you. Anybody else wants to comment? Jeannie, go ahead. Jeannie, go ahead and unmute.
You're muted.
Thank you, Don, for presenting. And what I really like about these models, and you really don't see it in other models very much, is how the action is emphasized. And I mean, we live in a world of motion and action. So I think it's very helpful to have models that can convey that idea. So thank you, Don.
Thank you,
I
Jeannie.
agree totally with that.
Thank
Thank
you.
you.
Next up is going to be okay, so folks. Firstly, I have put in chat the entire paper, the Tometry paper. So you can just scroll up in the chat and download it. You can just click on it and it'll open up on your computer. Okay, you can do that. Joe has just put a link to Don's book in the chat as well. Next up is going to be John and Yoshimi. John.
Yeah, I just wanted to say, Don, you're really twisted, and that's the best compliment I can imagine.
Yeah, I
Thank you
deserve
so
that.
much.
Yes, twisted and stable. So wonderful. Thank you. That was great. Joe, what did you think?
It's incredible, Don. I too am going to appreciate your ability to convey these complex ideas with models. Is very helpful for me. And I feel like you've actually put physics into context for me. So I think that that's really, it's a starting point. And you can start to see connections between a lot of things. So I very much appreciate that. And I appreciate your time. And I very much hope you come back.
Well,
Thank
thank you
you.
very much. That was very kind.
All right, folks. So thank you so much. And we'll see you soon. Bye, everybody.
Bye.
Bye. Thanks, Don.